On April 1, 2026, at exactly 22:48 UTC, the seafloor fractured 126 kilometers west-northwest of Ternate in the northern Maluku Sea. The United States Geological Survey recorded a magnitude 7.4 earthquake originating at a depth of 35 kilometers. This was a thrust fault. The Earth's crust snapped upward, vertically displacing the massive column of ocean water resting directly above it. Within minutes, Indonesia's meteorology agency, the BMKG, processed the seismic data, calculating a tsunami threat generating wave heights between 0.5 meter and 3 meters. An immediate alert went out across North Sulawesi and North Maluku, pushing residents away from the coast and toward higher ground. In a highly populated coastal region, survival comes down to the math executed in those first 300 seconds of automated processing. If you follow international reporting on Indonesia's disaster readiness, you will frequently hear that the country's early warning infrastructure is compromised. Specifically, critics point to a network of 22 deep-sea tsunami detection buoys, originally funded by Germany and the United States. Since 2012, that entire ocean-based network has been entirely defunct. Tech outlets and foreign observers routinely cite this lack of functional buoys as a glaring vulnerability that leaves millions exposed. Yet during the April 2026 Maluku earthquake, local authorities received an accurate, actionable alert with zero input from deep-sea buoys. The alert was issued by the Indonesian Tsunami Early Warning System, known as INA-TAUS. The Maluku event demonstrates the logic of the system architecture. INA-TAUS is deliberately engineered to mathematically bypass the open ocean. Indonesia sits directly at the tectonic convergence of the Eurasian, Indo-Australian, Pacific, and Philippine plates. Because the population lives right on top of these boundaries, almost every seismic event here falls into a specific category, the near-field threat. A far-field tsunami crosses an ocean basin over many hours. A near-field tsunami generates within 200 kilometers of the impact zone, like the Maluku epicenter, just 126 kilometers from shore. This near-field wave strikes the coast in 10 to 60 minutes. Deep-sea tsunameter buoys are designed to detect passing pressure anomalies in open water, providing coastal cities across an ocean with hours of advance warning. In Indonesia, the math works against that hardware. If a rupture occurs close to shore, by the time it registers on an offshore buoy, the leading edge is already destroying the coastline. Relying on physical verification here is a systemic dead end. The water arrives faster than the time required to accurately measure it. The Indonesian government engineered their solution around this near-field constraint, documenting it in the official INA-TAUS operational doctrine. According to Principle 4 of the guidebook, the system relies strictly on onshore seismographers, GPS earth plate deformation data, and coastal tide gauges. Deep ocean buoys are intentionally omitted from the critical path of the early warning decision chain. Instead of waiting for water to move, onshore seismographers instantly capture the raw frequency data of the Earth's crust fracturing.
This raw seismic data feeds directly into a processing algorithm known as the Decision Support System. Principle 5 dictates a strict processing window. The system has less than 300 seconds to calculate the magnitude, depth, and fault mechanism. The algorithm generates an estimated tsunami threat level from these inputs, pushing it directly to local governments. The evacuation mandate is triggered purely by mathematical Earth modeling. It does not wait for a single drop of ocean water to be measured. The April 2026 Maluku earthquake tested this seismic first model in real time. At T0, the fault ruptured 35 kilometers down. By T+5 minutes, the decision support system had finalized its calculations. The model projected a wave height up to 3 meters, triggering immediate regional evacuation alerts. This brings us to the final hardware component of the INA-TAUS architecture, the coastal tide gauge network. Coastal tide gauges do not provide early warning. Their true purpose is post-prediction verification. They measure the water as it hits the shore. This map shows the actual gauge data from the Maluku event. The network recorded 0.75 meters in North Minahasa and 0.65 meters in Kema. This physical data validated the algorithm. The wave arrived perfectly within the modeled parameters, at the lower end of the projection. With the threat accurately measured at the shoreline, the Pacific Tsunami Warning Center and local authorities safely lifted the alert. The Maluku event executed the system's design exactly as intended, substituting slow ocean measurement with fast seismic prediction and using the coast itself as the final verifier. While the automated system worked in April 2026, the seismic environment remained highly volatile, generating over 135 aftershocks, including a massive magnitude 6.2 event. The BMKG doctrine recognizes a hard limit to technology. No matter how fast a computer processes data, cell network congestion or power failures can delay the signal, allowing a 10-minute wave to beat a text message to the coast. To address this, the agency instituted Principle 11, which shifts the final fail-safe mechanism directly to the local population. Under Principle 11, the physical sensation of a strong earthquake is the primary, non-negotiable warning to evacuate immediately. Residents are instructed not to wait for sirens, SMS messages, or government verification. If the shaking is so violent that they cannot stand up, they must immediately move to higher ground. In near-field zones, the human vestibular system acts as the definitive early warning sensor, triggering an immediate survival response to the fracturing earth. When international observers repeatedly highlight Indonesia's broken buoys as a catastrophic failure, they are measuring the country against the wrong physics. That critique ignores the geometry and the extreme temporal constraints of the Ring of Fire. Spending millions to replace deep-water hardware would not buy Indonesian citizens a single extra second during a near-field rupture. The success of the Maluku response demonstrates an architecture built entirely around the acceptance of physical limitations. Resilience in the Ring of Fire is defined by the ability to mathematically outrun the water before the wave even forms.